So we have different formulas for the Doppler effect. Either the source is moving or the observer is moving. I have put them in the board here. This is a classical Doppler effect formulas. If the observer is moving toward the source, or the source is moving toward the observer, and this is a formula from special theory of relativity. The difference is the presence of the gamma factor, and here we have inverse gamma factor. And here this is solution when you resolve Maxwell's equation directly without any space-time transformation. We will get the same solution that we have for the classical Doppler effect formulas. But these formulas, they are for a medium that is not moving. When we have, for example, the V here is the speed of motion of the observer relative to the medium. And the medium, we consider the medium to be at rest, the system is not moving relative to that medium. And the same thing here for V. What happens if the observer and the source, they are in a moving system? What formula we are going to get? Recently we have published a paper. Its name is Electromagnetic Analysis Moving Structure in a Moving Reference Frame. And in that paper, we analyze the different Doppler effect formulas, and we compare with what we get in the simulation using Maxwell's equation. For example, in the first problem, let's consider that the system of the source and observer, all the system is moving with speed VE. Okay, and so that's the source and that's the observer. And we add a velocity to the observer toward the source. In that case, this one is moving VE, and here the observer is moving V observer R, I will say relative, minus VE, because I'm taking this direction. Okay, what is going to be the formula? The formula is going to be so we have a moving source VE and moving observer V or R minus VE. So here it's going to be 1 plus V or R minus VE over C divided by 1 minus VE over C. Okay, so that's the Doppler effect, F prime over F. And we can simplify this. If you see here the minus VE over C, we can put aside. It's going to give us 1 plus V or R over C divided by 1 minus VE over C. So if you compare this formula, so I didn't put the angle theta here for simplification. Okay, so we just put theta equals 0. So if we compare with this formula, it is the same formula, except we have this additional term here, which is the velocity of the system relative to the medium in the frame when the medium is at rest, so VE. But you can see that this term here is generally very small. It can be considered very small, so we can actually consider just use the usual formula. If now we consider a moving source. So let's continue. We can continue here. If now the source is moving, still the system is moving like this. The source is going to move VE plus VSR. So this is the speed of the source. R is for relative. And the observer here is moving minus VE here. So this is going to give us F prime over F equal. So we have here 1 minus VE over C for the moving source part, and here we have 1 minus VE plus VSR over C. So this one can also be simplified, and you're going to get 1 minus here VSR over C divided by 1, so minus VE over C. So the same thing, we have the same formula as previously, but with this additional term here. Now one can ask a question, when we use a Doppler radar, we have an object, a reflector moving, and we're analyzing the Doppler shift. What will happen if ourselves were moving relative to the medium? Does it change the Doppler shift? Or if it changed, by how much? So let's put it here. So we have the reflector. And the reflector here. So we have the source. The source is moving VE. The observer is moving VE in this direction. And the reflector is moving here V. So I put metal, so MR minus VE. Okay. So the formula here is going to be 1 plus VMR. So M is for mirror, sorry, not metal, mirror, over C. 1 minus VE over C. And here is divided by 1 minus V MR over C divided by 1 plus VE over C. We can use a first order approximation. So if we develop this, we can approximate the result, and we're gonna get, so this one is approximately, as we see here, is gonna be, so I put the result here, F prime over F. For the moving reflector, in a moving system, it's gonna be 1 plus 2 VMR over C. And this term here is divided by 1 minus VE over C, square and square here. Okay. So usually we don't have this term, so we have only this term here. This is the formula we use without this term. This is the formula we use for the Doppler radar. So we have 2 VMR over C here. So we have this additional term. Let's suppose we are the medium for light. We are moving relative to that medium. And what kind of velocity we can consider for VE? A maximum velocity. So in the paper, I will put the detail of the how we get this value. And we use, for example, a maximum velocity of Earth relative to the CMB, so the cosmic background. And we use a maximum of, so for VE, max, 800 kilometer per second. Okay? And we try to see how much difference it will make by if this motion will make in the Doppler shift. So I considered in the paper, we considered a car, for example, a car moving up at 100 kilometer per hour. So if a car VM is a mirror, is 100 kilometer per hour. What will be what we measure with the Doppler radar due to the motion or motion relative to the medium? So measured, I will say prime, we say M prime, is going to be using this 800 kilometer per second. Is going to be y 100.0.0.07 kilometer per hour. So instead of measuring 100 kilometer per hour, we're going to measure this, and you can see this is the difference is very small. So we can neglect this effect and just consider the relative motion between the source, between the object and the source. So this concludes this presentation. Thank you very much for your attention, and see you in the next video.